Hello, this is Dr. Hanaa Assil, and this is Unit 4 of the Pearson Edexcel International Advanced Level, and this was the paper of May-June 2024, so let us go through the questions and discuss the answers. This was the first question. It said, bromate ions react with bromide ions in aqueous acid, and we are given the rate equation. So according to the rate equation, we are told that the rate is first order with respect to bromate, first order with respect to bromide, and second order with respect to H+. And the first part says, which continuous monitoring method could be used to obtain kinetics data for this reaction? Now, which of these can we use? The first option here is colorimetry. You should remember that colorimetry is used if we have a change in color. Do we have a change in color? Yes, we do. Bromide ions are colorless solutions, but when they form bromine, you should remember that bromine is reddish brown, or we call it orange. So there is a change in color, and actually that is the method we can use. Okay, let's take a look at the other options. Can we use mass change? Remember that we use mass change only if a gas is given off, because that would mean that the overall mass of the mixture would change. Can we do titration with sodium thiosulfate? Remember, we're being asked for continuous method. Titration is not a continuous method, and there is no gas given off. What are the units of the rate constant for this reaction? Remember, if this is the rate equation, then we can write an equation for the rate constant K, and then put in the units for each of these. Rate, the unit is mole per decimeter cubed per second. So I can put mole over decimeter to the power 3 seconds. That's the rate. Now each of the concentrations is mole per decimeter cubed. So I have mole per decimeter cubed, mole per decimeter cubed, and mole to the power 2, decimeter to the power 6. This is how I usually do it. You cancel whatever is up and down, and what you're left with is the units for K. The concentrations of all reactants are halved. By what factor does the rate change? Now, this was the rate equation. If you're going to make each of these, instead of being 1, for example, it's going to be half, then you're changing it by a factor of 1 over 60. The first 4 steps in the reaction mechanism are shown, which is the rate determining step. Remember, the rate determining step is the one that includes everything in the rate equation, or it should be included above. So the rate determining step or above it should include everything that is mentioned in the rate. So I need the rate determining step and those above it to include once BrO3 minus, once Br minus, and twice H+. That would mean, and remember that if something is formed and then reused in the next step, then it is called an intermediate, and we can cancel all the intermediates. Now look at the reactants, at which step will whatever is in it or above it is included in the rate. So you should see that actually the rate determining step would be step 3, because by the time we get to step 3, we have gone through BrO3 minus once, H+ twice, and Br minus ones. Some data on the lattice energies are shown. Which compound has the greatest degree of covalency within its ionic bonds? Remember we said lattice energy can be obtained experimentally, or we can compare it to a theoretical value. Now, if the bond is purely ionic, then the experimental value should be almost the same as the theoretical value. But if there is a big difference between the experimental and the theoretical, we say there is some degree of covalency. It's not purely ionic. So if he's looking for the one that has the greatest degree of covalency, we're looking for whichever one has the biggest difference between experimental and theoretical. So just calculate the difference. The one with the bigger difference is the one that has the greatest degree of covalency. An enthalpy cycle for lead nitrate is shown. All values are in kilojoule per mole. The cycle is not to scale. First, he's asking which of these statements is true. So let's take them one by one. The first statement says the enthalpy change of formation of lead nitrate is minus 2151. Well, looking at this cycle, what is the minus 2151? Is it the enthalpy change of formation? You should remember, enthalpy change of formation is the enthalpy change that takes place when 1 mole of a compound in its standard state is formed from its constituent element in their standard state under standard conditions. So if I look at the one that says minus 2151, this is not obtained from its elements, it's actually obtained from its gaseous ions. So actually minus 2151 is the lattice energy, because that is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions. Enthalpy change of formation is from its elements. So the statement A is wrong. Minus 2151 is actually lattice energy. What about B? The enthalpy change of solution of lead nitrate is exothermic. Where is enthalpy change of solution? Enthalpy change of solution, first of all, should be the enthalpy change that takes place when 1 mole of an ionic solid dissolves in water. So I want ionic solid dissolving in water. So that is the arrow going up from lead nitrate solid to lead nitrate aqueous. And according to the cycle, it is plus 38 plus value of, or positive value for delta H is endo, not exo. So B is wrong. C, enthalpy change of hydration is more exothermic than that of nitrate. What is enthalpy change of hydration? It is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. So hydration is from gaseous ions to solution. Where is hydration to gaseous ions to solution? So the lead 2 plus to lead 2 plus aqueous and the 2 nitrates to lead nitrate aqueous. So he's saying the enthalpy change of hydration of a lead ion, that is according to the cycle minus 1485, is more exothermic than that of a nitrate. Well, the 2 nitrates give out less energy than the lead 2 plus alone, so this actually is the correct statement. Entropy change of the surroundings for dissolving lead nitrate is positive. Where is the entropy change of the surroundings for dissolving lead nitrate? Lead nitrate dissolving this, the delta H is positive. The statement says the entropy of the surroundings, or delta S surroundings, is minus delta H over T. So if the delta H alone is positive, then actually the entropy change of surroundings should be negative, not positive. Using the enthalpy cycle given, calculate the enthalpy change of hydration. Again, what is the enthalpy change of hydration? It is the enthalpy change when 1 mole of gaseous ions dissolve in sufficient water to give an infinitely dilute solution. So where is this? Enthalpy change of hydration. We said lead 2 plus gas going to lead 2 plus aqueous, and then 2 nitrates going to lead nitrate aqueous. So actually, if we're looking for the enthalpy change of hydration of 1 nitrate ion, we need to calculate it. Because remember, according to the arrows, minus 2151 plus 38 is equal to the other 2 arrows. And the one for the nitrates, that arrow, that blue arrow, is actually for 2 nitrates, not just 1. So if we're trying to solve for X would be the enthalpy change of hydration of 1 nitrate ion, and that comes out to this value. Ammonia is produced from nitrogen and hydrogen in the presence of a solid catalyst in an equilibrium reaction. Of course, this is the Haber process. 10 moles of nitrogen gas is heated with 30 moles of hydrogen in a sealed container. So this is what we're starting with. At equilibrium, we have 8 moles of ammonia. What is the total amount of moles of gas in the equilibrium mixture? So if we have a reversible reaction, we said initially we put 10 moles of nitrogen and 30 moles of hydrogen. Now remember that the change that would happen is minus X of nitrogen minus 3X of hydrogen to give 2X of ammonia. And that means that at equilibrium I will have the rest of that. But we are told already that what we have of ammonia is actually 8 moles. So the 2X represents 8 moles, and that means each X would be 4, and that means at equilibrium I have 6 moles of nitrogen, 18 moles of hydrogen, that's what is left, and the 8 moles of ammonia that were formed, and the total of that is 32. And we call this the ice chart, and we use this to get the number of moles for a reversible reaction. What is the expression for the equilibrium constant for this reaction? Remember, how do we write equilibrium constant? It is, for here it is Kp, so we're working with partial pressures. Remember, it is the partial pressure of products raised to the power of their coefficient over the partial pressure of the reactants raised to the power of their coefficient. So that expression in C is the expression for Kp. Which change would increase the value of Kp? We need to remember that any equilibrium constants, whether we're talking about Kc or Kp, does not change with concentration and pressure. The only factor that changes equilibrium constants is temperature. So decreasing the temperature, increasing the temperature, that would affect Kc or Kp. Any other factor will not affect the value of the equilibrium constant. For all chemical reactions, the equilibrium constant K is related to the total entropy change by this expression. Delta S total for a reaction is negative. So, for a certain reaction, the delta S total is negative. Which statement would be true? Now, for this equation to end up being negative, the value of the K should be less than 1. If you try on your calculator natural log of a number less than 1, natural log of 0.5, 0.3, that will come out as a negative number. Of course, R is a constant, it's not a negative number, so the only thing that would make delta S total negative is if the natural log of K is negative. A buffer solution contains ethanoic acid and sodium ethanoate in the ratio 1:4. What is the pH of the buffer solution? We're going to remember that this is the equation we use to calculate pH when we're talking about buffers. So pH is pKa plus log of the sodium salt over log of the acid. So if we're told that the ratio of acid to the sodium salt is 1:4, that means the log would be log of 4/1, and the pKa, remember that pKa is minus log of Ka. So we are given Ka, that means the pH would be minus log of that, plus the log of 4/1. It is a good idea to do each of them alone and then add them, because sometimes there is a mix-up in the calculator, but it's always a good idea to do them. That's how I do them. Anyway, so this is 5.4. The accumulation of carbon dioxide during exercise reduces the pH in cells and in blood. Which of these reactions is most important in buffering the decrease in pH that occurs? So we're asking which of these happens in the cells in order to buffer any decrease in pH. Remember that formation of carbon dioxide in the blood causes it to become acidic. This is because carbon dioxide dissolves in water to form an acid. So in order to buffer it, we need the opposite equation. We need the, if we have too much acid, then this reaction basically goes backward. How many chiral centers are there in the molecule shown? What do we mean by a chiral center? Remember that a chiral center is a carbon atom that has 4 different groups attached to it. So each of these carbon atoms has 4 different groups attached to it, and that means we have a total of 6 chiral centers in this molecule. The rate equation for hydrolysis of a halogenoalkane in aqueous alkali is shown. Which of these statements is true? So the rate is K times the concentration of the Rx, and this is first order. Now, which of these could be true? Well, let's take a look at this. Remember that hydrolysis of a halogenoalkane can either happen using an SN1 mechanism, in which the halogen leaves, forming a carbocation, then the hydroxide attacks. And remember that this happens if we're starting with a tertiary halogenoalkane. Now, if we had a primary halogenoalkane, we said this goes through an SN2, in which the rate determinant step, which is the initial step, involves both reactants. So the hydroxide attacks at the same time that the Br leaves. And in that case, the rate would depend on the concentration of both reactants. But when we say that the rate depends on the concentration of only the halogenoalkane, that means we're talking about SN1, and that means we're talking about a tertiary halogenoalkane. And the tertiary halogenoalkane, the mechanism involves a carbocation intermediate, which is a carbon atom that has a full positive charge formed when the Br leaves. This question says propanone reacts with HCN in the presence of potassium cyanide, and we're asked which of these statements is incorrect. Well, let's see. Propanone is a ketone. It has a carbonyl in which the carbon is slightly positive and the oxygen is slightly negative. The cyanide has a lone pair of electrons that attacks the slightly positive carbon, so actually the cyanide is acting as a nucleophile. So that first statement is correct. We're looking for which one is incorrect. Well, the second one says a racemic mixture is formed. Well, let's see. You should realize that a carbonyl is a flat planar structure in which the cyanide can attack from either side. So the cyanide can attack from the front and give one isomer, or it can react from the back and give the other isomer. But our problem here is the carbon that is formed from the reaction actually is not chiral at all, because the carbon has two methyl groups attached to it. We said chiral means we need 4 different groups attached to the carbon. So usually this reaction results in a racemic mixture, but because our original compound does not give a chiral center, so when we say a racemic mixture is formed, that's actually incorrect. So that is the answer we're looking for. When we say the product is not optically active, yes, because the product is not something that has a chiral center. The carbon is not bonded to 4 different groups. And when they say the product is 2-hydroxy-2-methyl-propane nitrile, this is actually how we name this product. Which statement is correct? We have ethanoyl chloride. So this compound is ethanoyl chloride, in which the OH of the acid is replaced by a halogen. So here we have reactions of ethanoyl chloride with what? We're reacting it with methylamine. Methylamine, the amine part, the nitrogen of the amine, has a lone pair of electrons that attacks the carbon, replacing the Cl. So this is nucleophilic substitution, and we have the product is N-methylpropanamide. So that actually, that first statement is correct. Now, if we react the ethanoyl chloride with dimethylamine, again, the nitrogen will attack at the carbonyl, replacing the chlorine, and the product is as shown in that question. So that statement is correct. What about if we react it with trimethyl? No, we do not react with trimethyl to give that compound. It will not react, so only 1 and 2 would react. An ester is hydrolyzed in excess dilute hydrochloric acid to form ethanol and propane dioic acid. Again, esters can be hydrolyzed either using acid, so the products would be acid and alcohol, or we could also use a base, but in that case it gives the sodium salt. So which of these, if we break the ester linkage, we end up with a part that's ethanol, and the other part is propane dioic acid. So these are the ester linkages that we should break up, and when we break it up, this actually gives ethanol and propane dioic acid. Now the others will not. This one, if we break it, this is ethanoic acid plus ethanol. This one would give propanoic acid. This one gives also the wrong answer. So A is my answer. Which compound has most peaks in its carbon-13 NMR? Well, remember the carbon-13 NMR gives different peaks for different carbons in different environments. So any different carbon would give a peak. Now that first choice, the methyl group on the right is exactly the same as the methyl group on the left. So both of them will give only one peak plus the peak for the CO. So this would give only 2 peaks in the carbon-13 NMR. What about this one? I have a peak for that methyl group on the left, and then a peak for the carbon of the carbonyl, and then the carbon of the CH2 next to it. All of these are different, so this would actually give 4 peaks. What about this one? This one again is symmetrical. I have a peak for the C double bond O, but both CH2s are identical and both methyl groups are identical, so we will both give just the same peak. What about in D? Again, we have the CH3, the CO, the CH2, and then the other part of the molecule is exactly the same, so they would give the same peak. So this is the one that would give the most peaks in its carbon-13 NMR. The high resolution proton NMR spectrum of an ester is shown. What is the formula of this ester? Now, first of all, looking at it, we need a molecule that has 3 similar protons and then 9 similar protons. Usually that means I have 3 CH3s that are identical and 2 similar protons. And remember that when the 2 protons are further to the left, that means they are next to an electronegative element like oxygen. So the 2 H's that would give rise to that peak after 4 is something that has CH2 next to O, to an oxygen. So which of these molecules would give, first of all, a peak for 3 CH3s? So it has to be C or D. A and B do not have identical CH3s. Now, is it C or D? Well, I want something with 2 hydrogens next to an oxygen. So this one doesn't, this one doesn't, this one has 9 hydrogens, but the 9 hydrogens are next to an oxygen. So if this were the case, then the peak for the 9 hydrogens should be further down to the left. So the one that applies to this one would be this. And then if you are not sure, you can look at the data booklet. If we have these ppms or these shifts for the peaks, you can check to see that this would be the correct answer. This question is about some compounds of silicon. Silicon dioxide and magnesium react when heated strongly. Complete the table indicating the type of bonding in reactants and products. So, silicon dioxide, what kind of bonding do we have? You should remember that silicon dioxide is actually a giant covalent compound. Magnesium is a metal, so the bonding would be metallic. Magnesium oxide is ionic with a large ionic crystal lattice. The entropy change of the system for this reaction is this value. Suggest with reference to the equation why delta S for this system is negative. We would like delta S to be positive, but we are told that for this reaction it is negative. Now, looking at the reaction, you should realize that it should be negative because we look at the coefficients and the coefficients tell you that before the arrow we have a total of 5 moles, giving a total of 3 moles. That means a decrease in number of moles. A decrease in number of moles means less disorder. That means the delta S of the system is negative. The enthalpy change for the reaction is this. Calculate the entropy change of the surroundings. You should remember delta S surroundings is minus delta H over T. We are given the value for delta H. The temperature is 23 degrees Celsius. Of course, we have to add 273 to change it to Kelvin. And that means this is the value for delta S surroundings. Of course, if the delta H is negative, the delta S surroundings comes out as a positive value. It's a good idea. Actually, you should put in the sign plus 1250. And what comes out here, because the delta H, please notice, and this is something that usually makes students lose marks, the delta H is usually in kilojoules. Now, we are required to calculate delta S surroundings in joules, so you have to multiply the kilojoules by 1000 to change it to joules. Calculate the total entropy change for reaction 1 at 23 degrees Celsius. Well, we know that delta S total is the delta S of the system plus delta S of the surroundings. We were already given the delta S of the system and we calculated the delta S of the surroundings. So just adding them up again, please put a sign before the final value and units. So units here are in joule per degree per mole. Then we're told reaction 1 does not occur at room temperature due to its very high activation energy. Suggest why the activation energy for reaction 1 is very high. So this was reaction 1, and when we're told that the activation energy for reaction is high, that means the bonds are very strong and they need a lot of energy to be broken. Remember that the silicon dioxide has giant structure with many strong covalent bonds that need a large amount of energy to be broken. Magnesium silicide reacts with hydrochloric acid forming silane and magnesium chloride. Write an equation for this reaction. So we just put in, remember that if it forms silane, then the other product should be magnesium chloride. Again, when we write any reaction, please remember to balance. We cannot leave the reaction without balance. Silane has a molecular structure. Complete the table giving the shape of a molecule of silane. Silane is basically silicon with 4 hydrogens. Remember, silicon is in group 4. That means it has 4 electrons in its outer shell. It's using them all, so there is no lone extra pairs of electrons on the central atom. You should remember this would be just like methane, in which we have 4 bonding pairs of electrons, no lone pair of electrons on the central atom. So this would be a tetrahedral structure with bond angle 109.5. Silane spontaneously combusts in air at room temperature. We have the entropies for each of them, and we're told to calculate the entropy change of the system. Remember that the entropy change of the system is the delta S of the products minus the delta S of the reactants. So just add them all up. Do not forget to take into account the coefficients. So just adding them up, and the products minus reactants will give this value. State why the entropy change of the surroundings for the reaction is highly positive in terms of the bond strengths of the reactants and products. So if we say that the delta S of the surroundings is positive, then that means that the OH bonds that are being formed are stronger than the silane bonds that are being broken. This question is about kinetics of the gas phase decomposition of ethanol. So ethanol breaking up to methane and carbon monoxide. Concentration time graph for this reaction is shown. Calculate the initial rate of this reaction. Remember, when we calculate the rate from a concentration time graph, we draw a tangent at the time we're being asked. So here we're talking about initial rate. That means at the beginning, at time 0, you draw a tangent, get its gradient or its slope. And remember, that means the difference in the y-axis over the difference in the x-axis. That is the rate. Now, we want it in mole per second. Mole per decimeter cube per second. Notice that the graph is giving it per minute. And that means you need to divide that by 60 to get it per second. Deduce the rate equation for this reaction at 1000 Kelvin by determining two half-lives. Okay, so if we have a concentration time graph, I can determine the half-life. Half-life is the time taken for concentration to become half of what it was. So from the graph, I can tell going from 0.6 to 0.3 took about 43 minutes. So this is the first half-life. Now I need a second half-life, and to get a second half-life I have to start from something else and get half of it. So for example, if I start from 0.4 and get half of it, how long did it take for it to go from 0.4 to 0.2? It's exactly the same half-life. Remember, if the half-lives are constant, that means the equation is first order, and that means the rate is equal to K times that reactant. Constant half-life means the reaction is first order. The rate constant for the decomposition of methanol was determined between 1000 K and 1700 K. The results are plotted, and we are required to determine the activation energy. Remember that the Arrhenius equation says ln K is minus EA over R times 1 over T times a plus a constant. So if we plot ln K versus 1 over T, the gradient or the slope is minus EA over R. So we get the gradient or the slope of that line, and always when you get the gradient of a line, it's a better idea to use as much of the line as possible. So for example, this gradient of this line is this. The gradient is minus EA over R, and that means EA is minus gradient times R. And putting the numbers in there, we get the value for activation energy. This question is about carboxylic acids and their derivatives. There are 5 carboxylic acids with the formula C4H6O2. 4 are structural isomers. One of these structural isomers has 2 stereoisomers. Name the 2 structural isomers shown. Of course, these are skeletal formulas, and you should be familiar with skeletal formula, this means we have 4 carbons, so this is actually bute with acid at the end, so this is butanoic acid. We start counting from the acid part, so that means at carbon number 3 we have an alkene, so but-3-enoic acid or 3-butenoic acid. You can actually write it in several ways. Again, the other one is 3 carbons with a methyl group on carbon number 2, so this is 2-methyl propenoic acid. The third structural isomer has 2 stereoisomers, so we're trying to draw something with 4 carbons and we want 2 stereoisomers. That means we need a cis and a trans, so these would be the 2 stereoisomers in which the double bond is in the middle. When the double bond is in the middle, I can draw it as a cis or as a trans. Draw the 4th isomer. So for C4H6O2, we already have all of these. So the only one that is left is if I have a cyclic compound attached to the acid. Some reactions involving 3-hydroxy 3-methyl-butanoic acid, and these are shown. And please notice the direction of the arrows in these kinds of schemes. Give the reagents and conditions for reaction 1. So where is reaction 1? This is reaction 1, in which we're changing the alcohol on the end into an acid, but we're not changing the OH in the middle. So we need this potassium dichromate sulfuric acid heat under reflux. It will oxidize the OH at the end because that is a primary alcohol, but it will not oxidize the OH in the middle because actually, if you look at it, that's a tertiary alcohol. Tertiary alcohols cannot be oxidized. Write the equation for reaction 2. This is reaction 2. So what do we have? We have this nitrile compound, and we're adding HCl, and we need to add water to give it more oxygens, and we are already given what the product is. Now what is the other product? It will be ammonium chloride, and again, do not forget to balance. Give the structure of the organic product formed in reaction 3. This was reaction 3. So if we are reacting this compound that has an acid part and an OH part, I'm reacting it with excess PCl5. You should remember that PCl5 can react with the acid. In that case, it forms acyl chloride. It can also react with alcohol to form the to replace the OH with the Cl. In both cases, you have HCl gas as a product, and this is seen as white fumes or steamy white fumes. So we have this with an acid part. The acid part at the end will become acyl chloride, and the OH in the middle will become a chlorine. So you can either write it as a skeletal formula or a structural formula. Give the structure of the organic product formed in reaction 4. This was reaction 4, where we have this compound that has acid and OH. We're reacting it with ammonia. And remember that ammonia would react only with the acid part, replacing the OH of the acid with an ammonium part. So either you write it structural or skeletal. This question is about some reactions of propanal and propanone. Now, they react similarly with lithium tetrahydrodoaluminate, and that's actually lithium aluminum hydride. So the formula of lithium aluminum hydride is this. Remember, to react with lithium aluminum hydride, it has to be in dry ether. Of course, lithium aluminum hydride is a reducing agent, so this is actually a reduction reaction in which the carbonyl becomes an OH. So if we're starting with propanal, we end up with the alcohol propane 1-ol. If we're starting with propanone, propanone has the carbonyl in the middle, so that changes to alcohol, so that would form propane 2-ol. State what would be seen when separate samples of propanal and propanone are warmed with Tollens reagent. Remember, Tollens reagent is a reagent that reacts with which of these? It reacts with the aldehyde. The Tollens reagent is actually a silver ammonia complex, and it would change from a colorless solution to give a silver mirror with the aldehyde but not with anything else, so no change with propanone. When propanone reacts with iodine in presence of aqueous sodium hydroxide, a yellow precipitate is observed. Remember, this is called iodoform test, and it is a test for the presence of the CH3C double bond O part. It can also react with CH3COH. So either we have a carbonyl on carbon number 2 or an alcohol on carbon number 2 would result in a yellow precipitate of triiodomethane, so CHI3, that is formed. That is the yellow precipitate. We also have the rest of the part as a sodium salt, and that gives an antiseptic smell. The other products would be sodium iodide and water. We are required to include state symbols, so please do not forget to include state symbols. The only thing that's solid in this is the triiodomethane, CHI3. Propanal and propanone both react with 2,4-dinitrophenylhydrazine. The products of these reactions may be used to distinguish between samples of propanal and propanone. Describe in outline the laboratory procedure for doing this. Remember that 2,4-dinitrophenylhydrazine is that compound on the left. It can react with aldehydes and with ketones, and when it forms that precipitate is actually a compound that is formed between the aldehyde or the ketone and the 2,4-dinitrophenylhydrazine. So that precipitate can be used to identify which aldehyde or which ketone we started with. So we can take that precipitate, filter, recrystallize, measure the melting point, compare to values in the data booklet, and I can use it to determine which aldehyde or ketone we started with. Propanone reacts with hydroxylamine under mildly acidic conditions. The first stage of the reaction is a nucleophilic addition. Add curly arrows to complete the mechanism for this reaction. So, we say we have nucleophilic, that means the lone pair of electrons on the nitrogen will attack the slightly positive carbon of the carbonyl. The electrons between the C and the O will go to the slightly negative oxygen, resulting in an oxygen that now has a full negative charge with lone pair of electrons, and the nitrogen is now bonded to 4 bonds, or has 4 bonds, so it's actually a positively charged nitrogen. So we're going to use the electrons to one of the hydrogens to change the positively charged nitrogen into a neutral nitrogen, and the lone pair of electrons on the oxygen will pick up an H plus to form the alcohol. Then we want to remove this water, so we're going to use the lone pair of electrons on the oxygen to form an O plus that has 3 bonds. Now use the lone pair of electrons on the nitrogen to release the positively charged oxygen. This gives this kind of intermediate in which we can use the electrons between the nitrogen and the hydrogen to form our product. This question is about acids and bases. Some Ka and pKa values for several weak acids are shown. Complete the table. So we are required to get the Ka from pKa and the pKa from a Ka. Remember that pKa is minus log of Ka. Ka is 10 to the minus of the pKa. So the Ka of that first acid is 10 to the minus of 525. So calculation, you'll find this from the calculator. The pKa is minus log of Ka. So that's what you do for that last acid. The structure of this compound is shown. Write the Ka expression for this weak acid. Of course, to write the Ka expression, I need to find the formula. So if you look at the compound, it has C5H5NH+. If it acts as an acid, that means it breaks up to give H+ and the rest of it. And that means the Ka would be the concentration of products over the concentration of the reactants. When methanoic acid is added to propanoic acid, an equilibrium is set up containing 2 acid-base pairs. Complete the equilibrium to label which of them will act as an acid and change into base, and which one will act as a base and change into acid. In order to determine which of these will act as an acid and lose the proton, the one that would act as an acid is the one that has higher Ka. Remember, higher Ka means the solution is more acidic, means that is the one that would lose the H+. So here, which one has higher Ka? It is the methanoic acid. The methanoic acid is the one that will lose H+ and become HCOO-. The propanoic acid is the one that will act as a base. It will take or accept a proton and become COOH2+. That means the one that is acid becomes a base. The one that is a base becomes an acid. So methanoic is an acid. It changes into B1. Propanoic acts as the base. It will change to A2. A student measured the pH of separate 0.05 mole per decimeter cubed solutions of these 2 acids. One of them has 1 chlorine, the other has 2 chlorines. The student also calculated the pH of these solutions, making 2 assumptions. So they measured the actual measured value and they calculated using the assumption that the H+ concentration is equal to the A- concentration, and that the concentration of the acid at equilibrium is the same as the initial concentration. Of course, these are approximations or assumptions, so the calculated doesn't come out exactly the same as the measured. Discuss the differences between the student's measured and calculated pH values. Now, we are given the Ka. Remember that an acid that has 2 chlorines is more acidic than an acid that has 1 chlorine. So the one that has 2 chlorines has a higher Ka. It is more acidic because chlorines or halogens are electron withdrawing. The more electron withdrawing atoms in the acid, the more acidic it is. Explain with reference to the assumptions made why there is a difference between the calculated and the measured pH values, and suggest why the measured pH values are higher than the calculated pH. So these are the values we are given, and we're also given the values for Ka, so we can use that to calculate. How did they calculate these pH values? Remember that we use that equation to calculate the concentration of H plus for a weak acid, square root of the Ka given times the concentration that we have up there, which is 0.05, and pH is minus log concentration of H plus ion. So the pH for that first one that has only 1 chlorine is 2.08. The same for the other one, the pH comes out lower. We said that is reasonable because the one that has 2 chlorines should be more acidic than the one that has 1 chlorine. Now, why the difference between calculated and measured? Remember that we had this approximation in which we said the concentration of the acid at the end is the same as the concentration of the acid that we started with, and that's really not true, because concentration of acid at equilibrium should be lower than the initial concentration because the acids dissociate. So calculated pH is lower than the measured actual pH. Now the difference for the CHCl2, the one that has 2 chlorines and the one that has 1 chlorine, we said this is because the presence of 2 chlorine atoms which are more electron withdrawing, so that makes that one more acidic. For hydroxybenzoic acid, a diprotic acid which dissociates in 2 stages, and we're given the 2 stages, in a titration, 75 centimeter cubed of 0.025 mole per decimeter cubed sodium hydroxide was added to 25 centimeter cubed of the diprotic acid. Remember, diprotic means when I draw the curve for the pH versus the volume, I should have 2 vertical lines or 2 sharp rise in pH. The first one should have, it should happen at 25 because 25 centimeter cubed of the acid would need 25 to neutralize the first proton and another 25 to neutralize the second proton. So there should be a rise or a vertical line at 25 of sodium hydroxide and at 50 of sodium hydroxide. Remember that the rise for the second one should be lower than the rise for the first one because of the pKa. So your graph should look something like this. A student was given 50 centimeter cubed of a solution of sodium hydroxide. The pH was 12.43. The student was asked to adjust the pH to 12 by dilution with deionized water. The student did not have access to a pH meter. Calculate the volume of water needed to add to the original solution in order to change it from pH 12.43 to pH of 12.00. So, concentration of H plus is 10 to the minus of the pH. So what we started with was pH 12.43. So my initial concentration of H plus ions was this. And that means the concentration of OH minus is 10 to the minus 14 over that. So this is the concentration of the OH minus in the original solution, and that would be the same as the concentration of sodium hydroxide. Now that means that the number of moles of sodium hydroxide that we have, concentration times volume, is this number of moles. Now I want to change it to pH 12. That means I want the concentration of H plus ions to be 10 to the minus 12. And in that case, the concentration of OH minus should be 10 to the minus 14 over 10 to the minus 12. So the concentration of hydroxide ions should be this. And that means the total volume that I need in order to have that concentration is 134.6. Now, we originally had 50. That means I should add 84.6 centimeter cubed of water. And that was the end of this. I hope it was useful to you. Thank you for listening.